Hi students, good evening. So today we are into the second session of laws of motion. So we are going to discuss about the idea of conservation of linear momentum, and then we look at the common type of forces that we are going to deal with in the laws of motion, and also we will look at some of the assumptions that we will be making with regard to the problems in laws of motion. Okay, so broadly we will try to cover the conservation of linear momentum. Then we look at what are some of the common types of forces, and then we'll also try to complete the assumptions in relation to the problems where we'll apply the laws of motion. Okay, so we'll start the session. So first we'll look at the idea of the conservation of linear momentum. So as I said, right, the conservation of linear momentum, this particular principle, we'll cover it here, and also we'll be covering it when we go to the system of particles. So we'll also take a look at this when we go to the system of particles. Okay, so first let us look at what is this idea of conservation of linear momentum. Already we have understood what is the linear momentum. What is the linear momentum, which will represent with the symbol P? It is nothing but mass times velocity of the object. It is nothing but mass times velocity of the object. Okay, so here we will define the law of conservation of linear momentum, not just for an object. So object means what? If you have a block, something like that. Okay, so if you have a person, we'll take it like an object. So here we are going to discuss about the conservation of linear momentum, not only for an individual object, but also for a system. So this word system is important, because whenever we are taking some objects together, when we want to study the objects together, right, we will consider them to be a system. Like, if you are studying the block separately, that is an object. If you are studying the man separately, that is an object. If you consider them together, then that is what we will be calling as a system. Okay, so we will be knowing more about how do we study the system when we go to the system of particles. But generally, in the context of this mechanics, right, say an object means that is one entity. When we say system, right, what is it referring to? A collection of objects like that. Okay, so look at the first, we will go through the statement of the law of conservation of linear momentum, then we will try to understand what this implies. Okay, so if no external force acts on a system or object, we are defining the conservation of momentum principle together, either for a system or an object. If there is no external force acting, means the total momentum of that particular system or object, whichever we are considering. This law we can either apply for an object separately, or we can apply for the system. The total momentum of the system or that object, whichever we are considering, is going to remain constant with time. What is it? This is going to be remaining constant with time. So this is what is the law of conservation of linear momentum. Okay, so now we'll see how we are going to understand this by using our Newton's laws, because this cannot be having a separate existence, right? It has to be something resulting from the Newton's laws. Okay, we'll see how we can understand this from the Newton's law. Say we have an object. Okay, so let us assume that the linear momentum of the object is given by what? P. Why are we putting a bar? Because it is a vector. Okay, now remember, what is the Newton's second law? So what is the general statement of the Newton's second law? The external force acting on that object will be equal to what? Rate of change of linear momentum, correct? External force acting on the object will be equal to what? Rate of change of linear momentum. Now here, if there is no external force, that is the case, right? There is no external force, means what? This derivative value is 0. There is no external force means what? The derivative value is 0. When the derivative value will be 0, when I take a derivative of any quantity, it is coming 0 means what? This quantity must be a constant. Then only the derivative will be 0, right? If you are taking a derivative of a quantity, it is becoming 0 means what? The quantity must be a constant. Means if there is no external force, means from the Newton's second law, see, the law of conservation of linear momentum we are not getting from somewhere else. We are getting it straight from the Newton's second law. Okay, so if there is no external force means what? The derivative is coming 0 means the momentum value must be a constant. Only then the derivative will be 0, correct? So if there is no external force, then whatever is the momentum of that object, or we can even use it for the system. We can even use it for what? So here we are calling it for one object. If you have a group of objects means that is system. If you have a group of objects means what? That is what is the system. In that case, what happens? The total external force acting on that system of objects, we will write it as what? The derivative of momentum of the system. Momentum of the system means what? Depending upon how many number of objects are there, we have to add up all the momentums. Momentum of the first object plus momentum, like that. We have to add up all the momentums. This is what is the momentum of the system. Okay. When there is no external force means what? This is 0. Which means what? The derivative of momentum of all the systems is 0. What does it mean? This sum should be a constant. Means what? The total momentum of the system of objects will be what? Constant. Means P1 plus P2 plus P3. The total value should be equal to what? Constant. Okay. So this is what is the law of conservation of linear momentum for the system. So either we can use it for one object or we can use it for the system of objects. Okay. Now as I said, we are going to study more about the same principle when we go to the system of particles. Okay. But here we'll just get the idea of what is this conservation of linear momentum, and we'll see some basic examples of where the conservation of the linear momentum will be applicable. Okay. Now when we see the conservation of linear momentum, what are we saying? It is nothing but a result coming from the Newton's second law, straight result coming from the Newton's second law. But what we will see is that this conservation of linear momentum is also going to be giving us an equivalent result to that of the Newton's third law. So Newton's third law says what? For every action there is an equal and opposite reaction, correct? So we will see how this conservation of linear momentum principle will be able to give us a result which is equivalent to the Newton's third law. So we will see, if you consider a system of two particles where there is no external force, in the absence of the external force. So there are two particles, let us call them as what? A and B. What are we calling them as? We are calling them as what? A and B. Okay. Now let the momentum of A is what? PA. Let the momentum of B is what? PB, like that. Okay. Now what is the total momentum means? What do you mean by the total momentum? Total momentum will be equal to what? PA plus PB. What is the total momentum meaning? PA plus PB. Okay. Now look at it. What is the Newton's second law if we try to apply? The total external force acting on the system. So here we are considering both of them like what? One system. Total external force acting on the system is equal to what? The rate of change of linear momentum of that system. System momentum means what? We have to add momentum of A and momentum of B, like that. But here we are considering that there is no external force acting on the system. Means from outside, no forces acting on either A or B. On A and B there are no outside forces acting. So that is the reason why total external force is what? 0. Now look at this. No, this derivative, remember we have done this in our basic math classes. Derivative we can split it, right? Derivative of PA plus derivative of PB, we are splitting it. derivative of PA. So because we can split the derivative, right? So when we split it, what is the rate of change of momentum of A? Now when you split it, what are we having? We are having rate of change of momentum of A plus rate of change of momentum of B. See, rate of change of momentum of A means what? This is the force acting on A. Okay. Rate of change of momentum of B means what? This is the force acting on B. Okay. Now remember what we said, on A or on B, there is no external force. Whether on A or B, there is no external force. Now, when there is no external force, what do you mean by force acting on A? What do we mean by the force acting on A? Force acting on A means what? This will be the force coming from B only, no? So this force acting on A is what? This is the force coming due to B. Similarly, on B also there is no external force. Means what? When we say force acting on B, this is the force coming due to A. Okay, so there are no external force means, when I say force acting on A means what? This is the force coming because of B only. When we say force acting on B means what? That is the force coming because of A. Now look at it. So what is this value? What is the value? This is equal to what? 0, right? So 0 is the total external force, that is the rate of change of total momentum of the system. That is what we are separating and writing. So the force acting on A plus force acting on B is what? 0. Now when we take any of them to the other side, what you are getting? Force acting on A is equal to minus force acting on B. Keep it. Which means what? There are no external forces. We are only having the internal force, like that. Internal force means what? Force acting on one object within the system due to the other object. Now the force acting on A and force acting on B, look at this. When we say force acting on A is equal to minus of force acting on B, like when you are writing two vectors, V1 is equal to minus V2, like that we write. What is the meaning of that? That means what? V1 and V2 will be negative vector of one another, correct? Similarly here, force acting on A and force acting on B, what they are? They are negative vector of one another. Means what? They will be having equal magnitude but opposite direction. They will be having what? Equal magnitude but opposite direction. Now just go back and think about the Newton's third law statement. What does Newton's third law state? If there are two objects, one object is creating a force on another, that second object will create a reaction which will be equal in terms of value but opposite in terms of direction. Check whether this is giving the same result or not. That is what it is saying, right? So here the force acting on A because of B and force acting on B because of A, what these two are? These are the action reaction pair, right? These are the action reaction pair. Now check it. What are we saying? The two forces will have equal magnitude but opposite in terms of direction. They have equal magnitude but opposite in terms of direction. Okay, so this is what is the relation between the action reaction pair. That is the reason why what do we say? The Newton's third law can also be derived, in the sense, not really derived, but the equivalent relation can be understood from the law of conservation of linear momentum, that principle, when you apply for a system of two particles or two objects. Okay, so this law of conservation of momentum, don't look at it like it is something different. It is something which is completely related to the Newton's laws. The statement or the result itself is coming from where? It is coming from the second law, and we'll see that this is also in correlation to the third law. When you apply this law of conservation of momentum for two particle system, what do we see? We'll see that this is in correlation with the Newton's third law. Okay guys, now we look at some very common examples. Look at this. If you observe this visualization, right, there is a man so who is walking on the boat, finally trying to jump onto the platform over here, shore. So when the man is jumping out of the boat onto the shore, what we'll generally observe, like in the visualization also you can observe what is happening to the boat. the boat is pushed slightly away from the shore. The boat is being pushed slightly away from the shore. You know why it is happening? Because here we will see that the law of conservation of momentum. The law of conservation of momentum is being applied. So why? Think about it. So we have a boat on which the person is standing. So this is the initial state. So initially the person is at rest. The boat is also at rest. Means what is the total momentum initially? So we are considering them as a system. So the boat plus that man, right? We are taking both of them to be like the system. When you take both of them to be like a system, right? Now what do you observe? This is a system. Okay. So what is the total momentum of the system? It is what? 0 initially. Now when you look at it, when this person is trying to move on the boat, is there any external force coming? No external force, right? So in fact, you know what happens? He will try to push the boat backwards. That is how he will be able to move forward direction. So the forces that are acting here are not the external forces. There is no external force acting. It is only what? The internal forces. Okay. Now, when there are no external forces, what do we say? The total momentum of the system must be conserved. The total momentum of the system must be what? Conserved. Which means, even when this man is walking on the boat in the forward direction, man will have a mass. He is moving with a velocity, means what? He will get some momentum. Let us call it as what? Some P. Because he is moving in the forward direction, he will get some momentum. If you take the forward direction to be the positive x-axis, just because we have to look at the momentum as a vector, then the man is getting some momentum. But the total momentum of the system must remain what? 0. Because that is what is the initial value. The momentum must be conserved. Means momentum is a vector, man momentum is in the forward direction like that. Then the boat should get a momentum exactly in the opposite direction. How much? Its value should be same, but direction must be opposite. So when the boat is moving in the backward direction, right, slightly it is pushed away, the momentum of the boat will be numerically equal to the momentum of the person. The momentum of the boat will be numerically equal to momentum of person, but opposite direction. When you add both the momentum, just try and add, what is it? P into I. This is the final. When the man is trying to move forward on the boat to reach the shore, final momentum will be what? P into I plus P into minus I. What is it? When you add both of them, we are still going to get 0, because after all the total momentum must be conserved. The total momentum must be what? Conserved. Okay. So this is how we'll see when the man is trying to move forward, the boat will get pushed back, so that the law of conservation of linear momentum is satisfied, because when there are no external forces, the total momentum of the system must be what? Conserved. Okay. So this is one example. And even if you happen to see people doing this ice skating, etc., we can think of the surface to be almost frictionless, because practically there will be no frictionless surface. Everywhere you will have some friction. Everywhere between the foot of that person and the floor there will be some friction. But this could be like an example of a very less friction surface, because we can never have frictionless surface. That is a very theoretical concept. Now when you observe these people, right, if they suddenly throw an object in one direction, like this lady, if she is holding some heavy object and she throws the object in the forward direction, if she is throwing the object in the forward direction, right, then the object will be getting some momentum in the forward direction. Initially the object is with the person, both of them are at rest. When the object is throwing the person, when the person is throwing the object, right, the object will get a momentum forward. But what is the initial momentum of the system? 0, right? Initially both of them are at rest, means the initial momentum will be what? 0. Now the final momentum also must be 0, because there is no, when the man is or the woman is throwing the object, means what? There is no external force, which means the final momentum also must be what? 0. You know what it implies? It implies that if that object is thrown forward, means you will see practically the person will be moving in the opposite direction. The person will be moving in the opposite direction, so that so he will move in the opposite direction with an equal value momentum but opposite direction. So vector wise, because momentum is a vector, right? When you add both of them, we are going to get what? 0. Now the extreme case of this, right, is even if you think the surface to be like a very smooth, like zero friction, then even if you are blowing air out of your mouth, like if you are blowing air out of your mouth, then look at it. So we are here, you blow the air out of your mouth. Air is what? Air is consisting of gas particles, right? So basically that will carry some momentum. When the air particles are going forward, means they will carry some momentum. Where is the air coming from? It is coming from within our body. So that is a part of our body initially, which is at rest. So to satisfy the conservation of linear momentum, right, we will see we ourselves can move in the opposite direction, and that is the extreme case. When it is going to happen? When imagine we are standing on a very, very smooth surface, like we should be almost close to that frictionless surface. In that case, we will be able to observe that even by blowing air, theoretically, right, if you blow the air forward, means what? The air particles will have some momentum in the forward direction. Initially the air is within our body, initial momentum is 0. So when you blow the air, you will see that you yourself will be moving in the opposite direction. So a person who is standing on a frictionless surface, right, can move by blowing air out of his mouth or by throwing some object in a direction. In which direction he should do it? He should do it in a direction opposite to the direction in which he wants to move. Like if he is blowing the air forward, means he will move backward. If you throw the object forward, means you will move backward. Okay, so always the movement of the person will be in opposite direction to the direction where he will throw the object or the direction where he will be blowing the air. Okay, so this is a very extreme example that you can see when we have a really frictionless surfaces. Okay, so this is about the conservation of linear momentum. Okay, and one of the numerical areas, because obviously it is not like we are always reading theory, right? We also have to look at the numerical problems. One of the numerical problems in this conservation of linear momentum is the recoil speed or recoil velocity. So what is it? Recoil speed or recoil velocity of the gun. So if you have the bullet and gun, so look at it. So if you have a bullet and gun as a system, before the bullet is fired, obviously this will be at rest. Before the bullet is fired, this bullet and the gun is at rest, right? Means when you're holding the gun, you will hold it at rest. So what is the initial momentum? The initial momentum will be what? It will be equal to 0. Now let us say small m represents the mass of the bullet and capital M represents mass of the gun. Small m is what? Mass of bullet, and capital M is the mass of the gun. If the bullet is fired in the forward direction with a velocity or speed v, bullet is fired in the forward direction with a velocity or speed v. Okay, velocity means we have to represent it like a vector v bar. Okay, now what is going to happen? Observe, the bullet is getting a momentum. What is the momentum? This is the momentum of the bullet. This is the momentum of the bullet, correct? Because it is moving with a velocity, it will have momentum. But when we look at the final momentum, because we are considering here the bullet and the gun as a system, when you look at how the bullet is moving forward, it is moving forward because of the force exerted by the trigger. So when you pull the trigger, right, because of the mechanism inside the gun, the bullet will be fired. And all this is what? Internal. There is no external force acting on it. There is no external force acting on it. It is all what? Internal. Now when there is no external force, remember, the total momentum of the system must be what? Conserved. Total momentum of the system must be what? Conserved. Which means when you look at the final momentum also must be what? 0. What do you mean by the final momentum? It is the momentum of the bullet plus momentum of the gun. So gun will get a velocity which we are calling as the recoil velocity. So we'll see what will be the recoil velocity of the gun. So let us say the recoil velocity of the gun is VR bar. What is the recoil velocity of the gun? It is what? VR bar. Now what will be the momentum of the gun once you fire the bullet? It is what? Capital M into VR bar. What is VR? This is the recoil velocity of the gun. Now this total momentum must be equal to what? 0. So see here, we are going to get some interesting relation. What is it? We bring it to the left side. Minus M into small m into V bar is equal to what? Capital M into VR bar. So we'll bring it to the left side. We'll go to the denominator. Minus small m by capital M into V is equal to what? VR. So this is what is the recoil velocity formula. So here this velocity of the gun, which you are calling as the recoil velocity, you can see what is it? Minus small m by capital M into V bar, means it will be in opposite direction to the velocity of the bullet. If the bullet is moving forward, means the recoil velocity of the gun will be in what direction? It will be backward. The recoil velocity of the gun will be in what direction? Backward. So the minus here represents what? The minus here is talking about the direction. The minus is talking about what direction? It is telling that the recoil velocity of the gun will be what? In opposite direction to the velocity in which the bullet is going to move. Now if you are just looking at the value, if you just want to know the value, so what we'll do, we'll take a modulus on both sides. Right? If you take a modulus on both sides, take a modulus, left hand side will be what? Small m by capital M into V will be equal to what? VR. This is only giving us the result for speed. What is it? This is what we call as the recoil speed. When you take a modulus, right, just giving us the relation between the speed of the bullet and speed of the recoil speed of the gun. What is the formula? Small m. Here, you know, we have to look at the notation. Small m means what? Mass of bullet, usually small. Capital M means what? Mass of the gun. Into V is what? The velocity of the bullet. That will be equal to the recoil speed of the gun. If you want to look at it in terms of the vector relation, this is what is the vector relation. This is telling us what? This is telling us the direction of the recoil velocity will be what? Opposite to the direction in which the bullet will be actually moving. Okay guys, so this formula is important. What is the formula? This is the recoil speed formula. Okay, now so while we talk about the recoil, right, it's not like, you know, it is very theoretical. This is something that people do have to be careful when they are dealing with guns. Obviously, you know, we don't deal with guns, but in countries like, you know, US and all, where there is a gun culture, right, people do carry gun, I mean, you know, quite frequently, because that's a allowed thing over there. So when you're firing a gun, right, if you are not holding it properly like this fellow, what is happening? The recoil velocity of the gun is actually, so he is not able to hold to it. The recoil velocity of the gun is making the gun to just move backward, and you know, if it is hitting in places like, you know, on your head or something, it can be quite dangerous also. So we have to be very careful. And you know, if you have a heavy machine gun, you will see that, you know, the person should have the capacity to hold that recoil. So if you are a lightweight person, you cannot be like, you know, going and start to fire with that heavy machine guns, because in case of heavy machine guns, the bullet mass will be high, and not only that, the bullet is also going to come with a very high speed. So you should be capable of holding that recoil. Okay, so all these things have to be taken care of. If you happen to be NCC student or something like that, right, you may get a chance to practice the shooting. Okay, but then, you know, you will be able to understand what is this recoil concept. So this is about the idea of recoil. We'll just go and solve one question before we move on to the next idea. Look at this, guys. A bullet of mass 50 grams is fired from a gun of mass 2 kg. So here we have to be careful about the units, because the mass of the bullet is what? 50 grams. And what about the mass of the gun? 2 kg. Units we have to be careful. A bullet of mass 50 grams is fired from a gun of mass 2 kg with a velocity of 500 meter per second. This is what? The velocity of the bullet. This is small m. This is capital M. Okay. What is the recoil velocity of the gun? So here, of course, they are asking us what? They are asking us the recoil speed. The value only they are asking. What is it? Small m by capital M into V, right? Small m means what? 50 grams. Means 15 to 10 power minus 3 kg. Divided by, what is the capital M? 2 kg. Into V is what? 500 meter per second. That's it, guys. So what is it? So we have, this can be written as what? 5 into 10. 10. This can be written as what? 5 into 100. See, 10 into 100 is what? 1000. The 1000 and 10 power minus 3 will be cancelled. So what is remaining in the numerator? 25. Denominator is what? 2. Kg is cancelled. So what is it, guys? So when the bullet is fired with a speed of 500 meter per second, look at now what is the recoil speed of the gun. It is just 12.5 meter per second. If the recoil is huge, then as I said, right, we will not be able to hold the recoil speed. So usually, because the gun mass will be heavy, right, the recoil speed will be what? Very less when you compare with the speed of the bullet. You can see here itself. What is the speed of the bullet? 500 meter per second. What is the recoil speed of the gun? Just 12.5. Okay, guys. So this is how we'll have questions on the recoil speed of the gun. Okay. Yeah, Sudhen, air rifle. So in NCC and all that, right? Like, you know, I've been a part of the NCC where when you go for a certain level of training in that, they will take you for the shooting practice. Okay. Of course, like it happens, right? You only, I think in my entire training, I just got a chance to fire 3 bullets. Okay. So you have to be like, you know, they'll show you the target and just 3 bullets is what you will get to fire. Okay. So you have to be making good use of that. Okay. Not sure, you know, how much of practice it will give, but nowadays, you know, you have a lot of other surrogate means. Instead of having the real gun, you have these, you know, we don't want to call it as a dummy gun, but yeah, for the lack of words, we can say there is, you know, dummy guns which will give you that kind of practice. Okay, they'll give you the same kind of recoil, etc., etc. Okay, so check it, guys. Are you getting this answer or not? What is the answer we should get? 12.5 meter per second. So those who are able to get the answer right, can you just type it over there so that I can also see whether you are able to follow the class or not? So this is it. In the recoil speed of the gun, right, only one formula we have, that's it. If there is a question, means good, because we will be able to just get the answer, you know, by using this one formula. Okay. Not sure, guys, you know, you will have to type the answer, then only I will know that you are able to follow. Okay. So then, you know, we'll go to the next idea. What is this next idea? The common types of forces. Check it, guys. Okay, so we'll go to the common types of forces. See, when we say common types of forces, right, we are going to talk about some of the very usual type of forces that we are going to use in the context of laws of motion. Generally, when we have to discuss about the types of forces, we have to discuss about all the types of forces, and this is exhaustive. So here we are going to just begin, and while we go to some specific problems, there also I'm telling you, we'll discuss about some other types of forces, particularly in some questions, right? We'll see some specific forces in the context of some of the problems. But here we'll focus on what are the common types of forces that we'll encounter. So first and foremost, right, is the weight. Remember, I might have told you that when we are discussing in the context of physics, the mass and weight cannot be used interchangeably, because in chemistry you might use mass and weight interchangeably. Like probably you will talk about gram atomic mass or gram atomic weight. You will say molecular mass or molecular weight, like you will be using them interchangeably. But in physics we cannot do that, because weight itself is defined. So what is the weight definition? Weight is defined as the force acting on the body due to the earth. Means here we are talking about what? The gravitational force. So what is the weight? Gravitational force due to the earth. That is what we'll talk about the weight. Okay, because we'll have the objects which are attracted by the earth. But if you go and take the object to the surface of moon, then when we say weight, that weight there will be what? The gravitational force acting on the object because of the moon. That we have to keep in mind. So here we are saying because the objects are on earth, the weight is defined as what? The gravitational force acting on that object because of the earth's attraction. And for the small objects we take, right, the earth is considered to be very large. So we'll consider the surface of the earth close to the object to be what? Horizontal or flat. Because the assumption is what? The objects are small objects. Small objects close to the surface. Small objects close to the surface, we'll see the surface of the earth to be what? Like a flat surface. When you go into the space and see, the earth looks like what? Some kind of distorted sphere. But when you're close to the surface and the object is very small, we'll see the earth to be like what? Flat surface. So what we'll see is that the weight will appear to be acting vertically downwards. Wherever you are or wherever the object is there, the weight will appear to be acting vertically downwards. And the weight will be measured as mass times the acceleration due to gravity. How do we measure the weight acting on the body? Mass times acceleration due to gravity. And since we stay close to the surface of the earth, we can take the value of g to be as what? 9.8 meter per second square. Sometimes we will also approximate it to what? 10 meter per second square, if we can get the answer in the rounded form. So if you want to look at the answers coming in the very much rounded form, we can even take the value of g to be as what? 10 meter per second square. But ideally we should keep it as what? Close to 9.8 meter per second square. Okay, so this is what is the value of acceleration due to gravity close to the surface of the earth. But if you go to some other planet or you go to the moon, there the g value on the surface of the moon or the g value on the surface of the planet will be different. This you will be learning in which chapter? Gravitation chapter. So which chapter we will learn about it? Gravitation chapter. Not only that, we are staying close to surface of earth. If you go to a considerable height, surface of earth, from the surface of earth, if you go to considerable height, then also the g will change. So in gravitation chapter we will discuss how the g value will change when you go to a height h above the surface. Not only that, g will also change when you go into the earth, like when you go to the depth d into the earth, right, there also the g will change. So we are going to talk about this also, how the g will change when you go to a height h above the surface and when we go a depth d below the surface. All this we will learn in the gravitation chapter. But here a simple assumption, we will take g to be equal to what? 9.8 meter per second square, or we can even sometimes approximate it to what? 10 meter per second square. This is the concept of the weight. Okay, now where does this weight act on the body? If you have a symmetric object, like usually what do we consider? We'll consider a sphere, or we'll consider a block, a cubical block, something like that. If you have a symmetric object, right, uniform, a symmetric object which is uniform, then we can represent the weight to be acting at the center of the object. We can represent the weight to be acting where? At the center of the object. Now we'll have a question, what if the object is not symmetric and not uniform? then the weight will be acting. So this is something that we will discuss when we go to the system of particles. See, all these things we have to keep in mind. So this concept we will discuss when we go to the system of particles. The weight will be acting at a point which we will call as center of gravity. What is it? Center of gravity. In system of particle chapter, right, we'll discuss about two things. One is center of mass, second is center of gravity. So the weight will be acting at which point? We will take the weight to be acting at the point of center of gravity. We'll take the weight to be acting at the point of center of gravity. Okay. So this is what is the difference that we'll see in case of the symmetric uniform object and the asymmetric ones. But this and all we can keep it aside for now, because we are going to mostly focus on what, like for us when we are dealing with the Newton's laws, we'll be given what? We'll be given the block, sphere, all symmetric objects only will be given to us. So where do we represent the weight? We'll represent the weight to be acting at the center of the object. We'll represent the weight to be acting at the center of the object. Okay. So all objects, whatever objects we see, whenever we are dealing with a problem in Newton's laws, right? Whenever we see object, the object is going to experience weight, which will be acting vertically downwards. What is the value of the weight? It will be equal to what? Mass of the object times acceleration due to gravity. That's it. Okay. So just for an example sake, if I ask you, there is an object of 4 kg. I ask you what is the weight. What will be the answer? What is the weight formula? W is equal to m into g, right? So m is what? 4 into g. If you take it as 10 approximately, then it will be what? 40 newtons. If you take g is equal to 9.8, we'll get slightly lesser value. Okay, so this is how we are going to do the weight calculation. Okay, so now the next important force is the force which will exist in a string or a thread or a wire or a rope. So when a string or a thread, this is not a spring, this is what? A string. When a string or a thread or a rope or a wire is held tight, like in this case, so there is a person 1, person 2, they both are holding the rope tight. The ends of the string or thread, whatever we consider, will be pulling whatever object attached to it. A rope, think about it. So you have a rope. This is a rope. Okay. Connected to the object. Rope will only be able to pull the object. A rope cannot push any object. So you take an example, right? Like you have a block. You tie a rope, you can pull it. But you tie a rope and can you push it? You can push it with a spring. Like you have an object, right? You take a spring, compress the spring, then you will see that object is going to get pushed. But with a rope, you cannot do that. If you keep a rod or something, like you keep a metal rod, there is an object, you keep a metal rod, you can push with a metal rod, you can pull with a metal rod. But with a rope, you can only pull things. So whenever you have a tight rope which is connected to the objects, the tight rope will pull, means it will always pull into the rope. Pull whatever body that is attached to it in the direction of that string. In which direction it is going to pull? It is always going to pull in the direction of the string. This force that will exist in that rope or that string is what is called as tension force. What is the force called as? Tension force. Like in this example, right? This is a tight rope. Now, what will be so the tight rope is attached to both person 1's hands as well as person 2 hands. The tension force acting on person 1, look at it. The rope will try to pull. What about the tension force acting on the person 2? That will also be into the rope. So always remember, the tension force will be acting into the rope. The tension force will be acting always into the rope. Okay. Now I can give you some of the other examples also. Look at this. If you have a rope, an object is here. Now the rope is connected to the object. How the tension force will be acting on the object? Look at it. So this is the point of contact. From here the force will be always acting into the rope. So this is how the tension force will be acting on this particular block. How the tension force will be acting? This will be acting upwards. The tension force will be acting upwards. Okay. Now look at this. You have a block. There is one rope connected above. there is one rope connected below like that. Okay, now look at it. The rope 1 tension force will be what? Into the rope like this. Let us call it as T1. And rope 2 is here, right? Rope 2 also will try to pull it into the rope 2. Like the tension force here will be what? Into rope. Everywhere the tension force will be what? Into the rope. Like you can see, tension force due to the rope 1 will be up in this case. What about the tension force due to the rope 2? It is downwards. Similarly, if you keep an object on an inclined plane, so this is what we call as the inclined plane. So what do we call it as inclined plane? We keep an object on the inclined plane, like there is a rope, imagine. Now how the tension force will be? This is the block. On the block, because we are connecting a rope to it, right? How the tension force is going to be? Tension force will be into the rope like this. Generally we will represent the tension force by the symbol T. Generally we will represent the tension force by the symbol T. Okay. Now you will have a doubt. Here the same object is connected to two different ropes. We are calling tension in rope 1 is what? T1. Tension in rope 2 is what? T2. What are we calling? Tension in rope 1 we are calling as what? T1. And tension in rope 2 we are calling as what? T2. When it comes to the example here, the first example we started, same rope is held by two people. The person 1 will also experience a tension and the person 2 will also experience a tension, correct? The rope will apply a force on person 1, rope will also apply a force on person 2. The question is, will these tension values be same or not? I am only saying the values. The tension force value, let us say here the tension force value is some 2 newtons. Is the value here also going to be 2 newtons or it will be different? Here we will just discuss about one assumption. We will talk about it again later also. If this rope or string, whatever you consider, is massless, can it be possible? Everything will have a mass, right? But this is an assumption we make. If the rope or string or wire you consider is massless, then tension everywhere in that string or rope will be same. Means what? Here two people are holding that rope, right? Tension everywhere will be same when that rope we are considering it to be massless. We know that is not going to be the case normally. Practically every rope will have a mass. But while dealing with the loss of motion problems, right? By dealing with the loss of motion problems, in most of the cases, we are going to make the assumption. What is it? The rope or the string or the wire, whatever we take, is what? Massless. This is the assumption that we make. We'll also look at problems where we will consider the rope to be having a mass. That also we'll discuss. But here one of the most common assumption is what? The rope is massless. If it is massless means tension everywhere in the rope will be same. Which means what? The tension force acting on this person, let us say, is T. Here we don't know the value. It may be 2 newtons, it may be, it can have any value. Then the tension force acting on the other person also will be what? Same T. Tension everywhere in the rope will be same when the rope is actually massless. Okay, so this is an assumption that we will be dealing, and tension force, right, will change depending upon the situation. Like if the rope is very tight, then it means what? The tension force is more. If the rope is less tight, the tension force is what? Less. You know, when the tension force in the rope will be 0, when the tension is going to be 0, when the rope is slacking. Slacking means what? When the rope becomes loose, or when the rope is cut. If the rope is cut means that's it, there will be no more tension in the rope. Okay, so tension is going to be 0 when the rope, we'll say, is slacking. So these conditions are important while solving problems, right? We will use the conditions like that. So when the tension is becoming 0 like that. So when they say rope is becoming slack or rope is cut, what it means? We will have to take the tension force to be what? 0. Okay, so this is about the concept of the tension force. Now yeah, maybe you can just make a note of this assumption. What is the assumption? If a string is massless, then what is it? Tension everywhere will be same inside the string. Okay, so we'll go to the next type of force, which is also a common one. About this force, We'll again discuss in this chapter work, power, energy, because this is going to be very much important in the work, power and energy chapter. So what is this force called as spring force? What is a spring? We already know. I'm sure we would have used the spring in different contexts. So if you have spring, you try to compress the spring or you try to expand the spring, because every spring, right, because of its geometry, it will come with a natural length. Every spring will come with what? Its natural length. When you try to compress it, you will see that when you're compressing it, you will see that there will be a force that the spring is applying on you. You know what you call this as? You call it as the resistive force or restoring force. You call it as what? The resistive force or restoring force. Similarly, you think about elongating the spring from the natural length. Again, you will see that there is a force that is trying to pull the spring back. So if you compress the spring, means the spring will try to push you away so that the spring can go back to the natural length. If you are trying to elongate the spring, means what? The spring will try to pull back so that it will go back to the natural length. It will try to pull it back. So this resistive force that opposes any attempt to the change of the length, the spring will oppose any attempt to the change of the length of the spring. When you say length of the spring, we are talking about the natural length of the spring. This force is called as the resistive force or restoring force. What do we call it as? We'll call it as what? The resistive force or restoring force. Now, why are we discussing about it in the laws of motion chapter? Because think about it. You have a spring. We are connecting the spring to a body. That is where it comes. So here this object of mass m, a block or whatever we call it, is connected to the spring. When the spring is in its natural length, we are marking the position of the block to be x is equal to 0. When the spring is in the natural length, we are marking the position of the block to be what? X is equal to 0. In that case, the spring will not exert any force. When the spring is in natural length, it will not exert any force. But if we try to elongate the spring, elongating means what? Look at it. We can see how much elongation has happened. How much elongation has happened? X amount of elongation has happened. So we move the block by a distance x like that. Then what is the elongation in the spring? The spring is also elongated by the same amount. What is the elongation in the spring? X. So we can measure the elongation in the spring by the displacement of the object. So x represents what? The displacement. X represents the displacement of the object. So we can measure the elongation of the spring also by the displacement here. Okay. Now when there is a displacement x that we are giving for the mass, this mass will experience a force. Look at it. So you have a spring, you elongate the spring. The spring will try to pull it back, right? Look at this. The spring force will be acting in the opposite direction, you can see. So if the block is displaced right, spring force acting on this will be towards the left. And when you look at the property of the spring, right, what you will see is that the resistive force will be directly proportional to the change in the length. Means what? If you look at the force that is developed in the spring, that is the force the spring will be acting on the block. That force is what we are calling as the resistive force or the spring force. The spring force will be proportional to x value. Okay, but in terms of direction it will be what? Opposite. In terms of direction it will be what? Opposite. So if you have any proportional relation, right, we can make this into an equation. This is what is the equation. So just make a note of it. This is what we call as the equation for the spring force. What is it? The equation for the spring force. We can see two things. One, the spring force will be in opposite direction to the displacement. Means we are displacing the block to the right side, means the spring force will be acting towards the left side. Not only that, the spring force is directly proportional to the change in length of the spring, because change in length of the spring is given by what? The magnitude of the displacement. Whether you move the displacement to the right or left, we look at only the change in the length of the spring. Change in length of the spring is given by what? The displacement magnitude. Okay. So this is what is the equation that represents the spring force. So the spring force will be opposite to the direction of displacement of the block. If you displace the block to the right side, means spring force in this case you can clearly see it will be acting to the left side, and this constant K here, right, will change from spring to spring. It will be a property of the spring. The constant K will be what? It will be a property of the spring. We will call it as spring constant or stiffness constant. What is this K going to be called as? K will be called as what? The spring constant or stiffness constant. We'll talk about this K in a little while, but this is what is the equation for the spring force. Now we have seen one side of the story. What is the other side of the story? When we try to compress the spring, look at this. If you want to compress the spring, means we should move the block to the left side here. From that x is equal to 0, when we go to the oscillation chapter, right, you know what we call this x is equal to 0 as? We will be calling it as mean position, like that we will call, where when we go to the oscillation chapter. Okay, so from that x is equal to 0, the natural length position, we move the block to the left. Then what you are going to observe, look at it, when you compress the spring, means spring will try to push you back. So the spring will apply a force on the block which is towards the right side. So here also you can see the displacement to the left, spring force is right. Again the same formula. The formula is valid whether the spring is getting compressed or the spring is being expanded. Always F will be equal to what? Minus K into X. If you just want to look at the force magnitude, the magnitude of the spring force, that will be given by what? K times X. Here we will say X is what? The amount of elongation or compression. Here X will represent what? The amount of elongation or compression in the spring. This is the equation for the spring force magnitude. Okay, so this force that will exist in the spring, which will always try to take the spring back to the natural length position. That force is called as what? The resistive force or the restoring force. What is the magnitude of the restoring force given by? F is equal to K into X. Means we elongate the spring more, the magnitude of the spring force also will be what? Increasing. This is something that you can practically check. Take a spring, just elongate it, you will feel small amount of force. You elongate it more, you will see a large amount of force. Same thing can be seen in the case of the rubber band also. Take a rubber band, just try to pull it. You will see that there is a force acting on you, but not much. But you try to pull it more, then you will see that there is a large amount of force acting on you. Okay, so this is about the idea of the spring force. So whenever a body is connected to the spring and the spring is either elongated or compressed, then we will have to see what is the spring force acting on that body. Okay, now we are talking about the spring constant, right? See, whenever we get a new constant, we should try to understand about the constant. So every spring, based on its design and the material properties, it will possess a value of the spring constant based on what? The geometric design and the material property also. Like you have a spring made up of copper and you have a spring made up of some other material. Though both of them will have the same geometry, they can be having a different value for the spring constant. Okay, so if they have the design and the material properties is something that is going to determine what is the value of the spring constant. But here we are not going to get into the details of how exactly the spring constant value will come and all that. But here let us just take a look at what is the SI unit, because we are talking about a constant, and what is the dimensional formula. See, we have one equation, right? The spring force magnitude is equal to what? K into X. From this, what is the force SI unit? Newton is equal to K into what is X representing? Amount of elongation or amount of compression, means what is it? Meter, right? So look at it, the meter will come to the left side. So what is the SI unit of the spring constant? It is Newton per meter. Similarly, what will be the dimensional formula? Same equation we take. This equation, right? What is there on the LHS? Check it up, guys. What is there on the LHS? Force. Force means what? mLT power minus 2 is equal to K spring constant into X. X is what? What is the dimensional formula for X? X is the length, right? Elongation means L. So you can see L is cancelled. MT power minus 2. This is the dimensional formula for K. So whenever we get a new physical quantity or a new constant, always we should keep an eye on what is the SI unit of the quantity and what is the dimensional formula for the quantity. Okay guys, so probably we'll stop the class today here, and in the next class, right, we are going to continue our discussion about some of the other common types of forces, and then we'll continue from there onwards. Okay guys, we'll see in the next session. All the best.